minus v tangential squared over r, right? V squared over r, where v is your tangential speed. That's perpendicular to the centripetal direction. Right? So the centripetal, so this is the first time you saw any crosstalk between your dimensions. Right? You have something happening in one dimension, the tangential, that affects the centripetal dimension and vice versa. Normally we throw the negative sign away. It's a convention that towards the center is negative. If you forget that, just remember gravity is always down, but really if you zoom out, gravity is towards the center of the Earth. That's down, we call that negative. Gravity actually turns out to be a centripetally directed force. Down is negative, towards the center is the conventionally defined as negative, right? You can change it if you want to, but you gotta know what you're changing before you change it. So we typically get rid of the negative sign. I won't worry about it here. So this leads us to Newton's second law, expressed in the centripetal tangential coordinate system, right? So instead of an x or y, I just subscript this with a c. And then I sum up whatever forces are acting in the centripetal direction. In this case, it's just magnetism. We're ignoring gravity. I'm assuming my charged particle is really small. So we're going to ignore gravity. And I just get Q, V, B. It's just the magnitude, right? I threw away the vector nature. The sine of theta, which comes in from the definition of cross product, just gives us 1 because these are already perpendicular and the sine of 90 is 1. So this is what I have as far as a centripetal force. And that equals, this is the left-hand side, that is equal to m, a centripetal. Again, I'm going to get rid of the negative sign. I'm just going to define towards the center as positive. I need more room. I think I can erase it. All right. I get Q V B is equal to m v squared over r, where v is the same, right? It's a tangential velocity, but that's all I've got here. This is nice. I get rid of this one, I get rid of this one, and I get this expression. QV is equal to mv over r, where r is the radius of my circle. Okay. Interesting things happen here if I solve for different quantities. Let me solve for v over r. Basically, I'm just moving the m over. So those of you that really paid attention to centripetal tangential coordinate systems and rotational motion in 1600, which was none of us, right? I didn't when I was there. Anybody recognize v over r? This is a linear quantity, v over r. What does that turn into? What's that? It's not a W. What is this? Omega. Omega. What is omega? Rotational velocity, right? This is your translation formula between linear quantity velocity and rotational velocity expressed in radians per second. Has to be expressed in radians per second for this to make sense, right? So V over R is just your angular velocity, right? This means this thing will flip around in a circle at an angular velocity given by Q V over M. It's called the cyclotron frequency, if that is interesting to you. But this is actually really a useful formula. In your lifetimes, the Large Hadron Collider has made some pretty cool discoveries. When I was a kid, sitting where you were, the Large Hadron Collider wasn't even operational, right? Now they've discovered lots of cool stuff. And so every now and then you'll read about scientists in Geneva have discovered a new particle. It has a mass of so-and-so. How do they know? Like, how do they know how much mass this particle has? They don't have tiny scales. That's not how it works, right? This is how they know. If they can measure the charge of the particle, what they do is they send it into a magnetic field. It's actually really cool. I'll diagram it out for you. They have a magnetic field that they have done a good job of canceling every they have a hole here, and they send in some charged particle at some v. As soon as it hits the magnetic field, it experiences a magnetic force and begins to move, and because they oriented the magnetic field perpendicular to where they're sending in the particle, it starts to move in a circle. So it comes in, bam, hits the wall. Okay, all they have to do is measure. This is 2 times the radius of the circle, right? So if they can measure this, they know what the radius of the circle is, right? If they know the velocity, which they do through other means, which we'll talk about later, then they know the angular velocity. So if they've already measured the charge, they control the B field, right? The only thing that I have to figure out is the end. They just measure the radius, then they can determine the mass of the particle. This is actually how this is done. It's a very, very, very practically useful thing. If you're somehow able to just materialize the particle inside this field, it'll just turn in a circle forever, as long as it's oriented perpendicular to the magnetic field. Okay? Questions about that? This formula is on your formula sheet, but you should be able to get there. You might have to go back and review centrifugal tangential stuff, but that's okay. Any other questions, or any questions about that? Okay. So if we have a particle, a charged particle, remember if there's no charge, this force is 0. If I have a charged particle that is inserted into a magnetic field traveling at a velocity that's perpendicular to the field, the thing just moves in a circle. What if it's not exactly perpendicular? Well, good question. So let's see if I can do this. Here's my magnetic field. And let me put a particle in here. I'll just make it positive for the interest of ease. And there's my velocity. Right? So it's going to experience a force which is only based upon the perpendicular component. Right? That's what our cross product does for us. It throws away the parallel components. And please understand, I'm not saying it experiences a force based on the perpendicular direction because the cross product says it's supposed to. That's not how it works. The universe gives it to us, and we describe it mathematically with the cross product, right? So it experiences a force based on its perpendicular components. That's just how the universe works. Then we come in and describe it with the cross product, right? So I'm not saying math governs the universe, although physicists talk like that a lot, myself included. Math doesn't govern the universe, math describes the universe. At any rate, we can describe it with the cross product. So let me peel off some components here. Here is the parallel component. Here is the perpendicular component. We'll call this V parallel. We'll call this V perpendicular. QVB then is going to be just Q V perpendicular V. Magnetic force by magnitude QVB sine of theta, right? So this is the definition I said wasn't particularly useful, but it's okay here, right? Well, V sine theta, theta is what? Theta is measured between V and D, right there. Right. And we're going to throw, basically that picks off the perpendicular component. This is the same thing as writing this. Right? Which is probably a little bit like how you handle torques when you're doing torques. Nobody actually wants to do the trig. We just want to pick off the perpendicular component and say that that's what produces the torque. Same thing is happening here. The force is going to be just based on the perpendicular components. Right? So this one determines the magnetic force. So this thing is going to start to turn in a circle that is perpendicular, I should say, has a radius which stays perpendicular to the velocity in the B field. right? And that, I can't really show it to you on the board. What that means is as this thing moves into the field, it starts moving in a circle like this. There's the magnetic force. It's going into the board, out of the board, into the board, out of the board. But it still has a parallel component. This doesn't affect the force, but it doesn't get canceled by the force either. So it comes in, and the perpendicular component gets turned into this motion, but the parallel component stays, and so the thing does this. It corkscrews. It just forms a big helix. Right? A charged particle that enters the magnetic field will it will describe circular motion. But if any component of its velocity is parallel to the field, it will describe circular motion, but also translate down the field line. Okay. Anybody ever seen the Northern Lights? This is how they happen. Right. Charged particles from the sun interact, which the sun is constantly producing charged particles. It's called the solar wind. They interact with the Earth's magnetic field, and many of them get trapped in this situation. They will come in at some angle to the magnetic field, and they will start corkscrewing. And there's some other really interesting magnetic phenomena we don't have the time to get into. They will a lot of times bounce back and forth between the poles for a long time. They'll corkscrew around into the North Pole, corkscrew into the South Pole, back and forth. If they come into the atmosphere at just the right angle, though, they get into the atmosphere, interact with chemicals in the atmosphere, interact with elements, and produce light. Right? This is where the northern and southern lights come from. But they're predicated upon this interaction between the charged particles from the sun and the magnetic field of the Earth. Any planet with a magnetic field has aurora. Jupiter has phenomenal aurora. You can Google online Saturn. They all have aurora because they all have magnetic fields that trap charged particles using this magnetic force. Okay? That's not such a pretty situation because the field isn't uniform. So you get lots of interesting things. But this is actually some other really interesting physical applications. Trapping charged particles in magnetic fields is standard in lots of fields. Most notably at this university, in our department, we do a lot of fusion plasma research. Everybody's goal at this point is to kickstart fusion energy production, right? Fission works just fine, produces a lot of byproducts. Fusion would be more energetic, produces fewer byproducts. The problem is how to start it, right? So everybody's trying to kickstart fusion reactors. Part of the problem with fusion is you have really high energy particles. It's all hydrogen. It's not toxic or anything, but they're really high energy, meaning you're moving very fast. And you have to keep them contained in your chamber in order to have them hit each other and start to fuse together. How do you keep them contained? Well, you ionize them, which means you make them into charged particles, and you use magnetic fields to contain them, right? Just like the Earth's magnetic field contains these charged particles. It's called magnetic bottling. If you've ever read anything about people doing experiments with antimatter, antimatter can't interact with normal matter. It annihilates in a large energy production. It's the most energetic reaction in the universe that we know of. Antimatter annihilation. How do you contain antimatter? You can't let it hit normal matter. Magnetic bottling. Right, same deal. So this is a lot of really interesting applications come out of this. Not just physics application, engineering application. Trust me, in experimental physics there are tons of engineering positions, right? Tons of stuff that have to be created with a really good knowledge of the physics and a good knowledge of the machinery. So this is really very common stuff in a lot of fields. Containing charged particles in plasma. I mean, they do it in television, right? Plasma televisions actually use plasma and charged particles. Old CRT monitors formed images by redirecting charged particles with magnetic fields to hit a phosphorescent screen. So this stuff is all over the place. This is really important stuff. All right, any questions on any of that? Okay. Give me 2 seconds. Actually, got more done today than I thought, so let me see where we any of you have questions about the exam, about the stuff we're doing today, please ask. About the right-hand rule. Bad joke. Just a couple more things we can get done today. Finish up this chapter next time. So, we've been talking to this point about currents, right? Our whole last chapter was on currents and voltages and things like that. So, what is a current but a collection of charged particles? Specifically, what we consider a current is a collection of positively charged particles. Now, again, we know in the back of our minds that in a wire, positive charges are not what's moving, it's negative charges. It just turns out it doesn't matter. It's easy for us to think about it as a motion of charged particles in one direction as opposed to a motion of negative particles in the other direction, which is what it actually is. We just don't care because the math works out either way. We picked out the easiest one. So, a current then is a collection of positively charged particles moving in overall in the same direction. Again, we know if we go inside this wire, the particles are bouncing around, but overall they have an average velocity that's this way, right? Okay, well, what happens when we put that inside a magnetic field? Well, each of those particles are going to feel a force, right? It's not so bad because they're all positive. We have this. I'll do it forward. This is the force on an individual particle. If I put together all those particles and allow it to move more or less in a straight line, right? At least on the average in a straight line. It doesn't have to be a straight line, we'll keep it simple. That is to say, down a wire. I can actually write this. And let me see how you both write this. Make sure I do this. Alright, I'm going to give you this and we'll talk about it more next time as well. Okay. This is, I will say, usually given to you in differential form, which we'll talk about later. But let's see if we can match up what we see here, what we've already seen with what our new stuff. So, the magnetic field stays the same. No big deal. Q has now become I. That's okay, because all I is a motion of Q. Right? So, in some sense, this is actually easier because when I had Q, I had to think about positive or negative, right? This is always positive. So I always can do, when I do the right-hand rule, I always consider these to be a movement of positive particles. So what is this L? Well, L is a vector, and I'll write this down. L is a vector directed along the conductor. You can kind of see what's going on from the units here. If I look at these units, I got a coulomb from the charge and a meter per second from the units, from the velocity, right? Well, if I look at these units, I've got a coulomb per second from the current, right, dq dt, and then 1 meter from the length. So see, all we're doing is we're playing around with the units, and then reformulating different things based on the same units, right? They have to have the same units, because on the left-hand side, I got to get a Newton in both cases. This is just how we formulate it. Instead of looking at a force on one charge, we look at a force acting on the entire wire. Now, this can get a little sketchy because there's no guarantee that you have a straight wire, right? So, generally speaking, you will see this given in differential form like this, dF. That is to say, the small contribution to the overall force due to a small section, a differential section of your conductor. Just like this. And then you're going to integrate this along a particular path. If it's just a straight line, this differential form is going to reduce down to just that, right? The good news is for you guys, we don't do a lot of complicated geometry in this course. We're going to integrate over straight lines and around circles, and we've already done that. It's no big deal. If you have a wire that goes in a square, though, or some sort of geometrical shape, though, this just turns into integrating along one line and adding it up to the integral along another line. And so I mean, integrals are just summations, right? So you can integrate over 3 different paths and add them together. So we handle the simple cases in here. This is how you will most often see it written, but that is valid. Now, in the cases which are frequent, which I and B are always perpendicular, we like to keep it simple in this class, right? So if I don't have any crazy angles, this reduces down to the scalar version, ILB. And that, of course, is the simplification, recognizing that the length of the wire is oriented perpendicularly to the magnetic field, and it's not moving, right? If it moves, I got to do the calculus. If it doesn't, and I just have a simple section, I can use that equation. You determine the direction of this force exactly like you do a charged particle with the right-hand rule. So let's do an example of that. Here's your magnetic field. Pointed out of the board at this point, at this time, I should say. And let's put in a long current-carrying wire. It's carrying a current in that direction, towards the right. Y'all tell me, do it. Do the right-hand rule, recognizing that these are just positive charges. What direction are you going to get for the force exerted on this wire? Yep, you're right. Down. Yep. I get a direction down. Fingers in the direction of the current, right? In the direction of the velocity, but the velocity goes with the current, so that goes this way. And then I curl them towards the field, which means I have to turn my hand over and curl them out of the board. I stick out my thumb. I don't have to check any charges because they're all positive. I get a force down. So in this magnetic field, this wire goes down. This is also something you have to take into consideration if you're building currents that are existing in magnetic fields. We're going to find out later that currents produce magnetic fields, and so if you have a current, you're going to have a magnetic field. And sometimes it's important to be able to consider this force. Sometimes it doesn't. It's negligible, but it's something you got to be aware of. All right. Any questions about any of this? That was kind of a whirlwind through chapter 11. We got a little bit more to do on it, but any questions so far? If you haven't read chapter 11, please do so. I will tell you, traditionally, most everybody agrees that the difficulty